Welcome to the seventh part of our forces unit, where we now talk about specifically the elastic force. Now this is a very specific force in terms of when we see it pop up, and that's whenever something is being stretched, compressed, or twisted. The reason that we see that is all materials always want to be in a specific rest state. If we try and disturb that, they want to go back to it. So you have to apply a force to stretch it or compress it or twist them, and then that force is stored in the elastic as a potential force. And then if it's allowed to go back to that rest position, that force can then be released. We see problems like this most commonly involve elastics and springs, but just about any material can truly be stretched, compressed, or twisted, but sometimes they will break before you actually see that happen. So, in terms of relating the force to how much something can be stretched or compressed, we actually get a linear relationship between those two. So if we have the force as our dependent variable, and then the amount of stretch, which we're going to label as x, the relationship will always follow a linear pattern for simple situations. If we go to extreme situations, this law does not stand, but in everyday situations this is approximately true. So we get that Fe, our elastic force, depends directly on the length that the object has changed. But the problem is that doesn't give us an equation. We saw this before with Newton's second law, where we had to make an equation and there was a constant. That constant ended up being 1 for Newton's second law, but in this case that is not true. We just get Fe equals kx, and this is known as Hooke's law, where k is some spring constant which is unique to every material. So it is unique, and the units are newtons over meters, and x is the length stretched or compressed from that rest position. So whatever it wants to be at, if we change it from that, then we have some elastic force. We can see some spring constants here for certain materials, and things that we can stretch easily, such as rubber. You see that it's down there at 700 newtons per meter, so it takes 700 newtons to stretch a piece of rubber 1 meter. That's the idea of that spring constant there. And then you can go all the way down that list and end up at diamond, which takes 120 times 10 to the 6 newtons to stretch it 1 meter. So that's quite different. And this really follows logic because it's easy to stretch rubber materials, whereas diamond we don't think as a material that is stretchable. So let's look at an example. We have a steel spring of spring constant 40.0 newtons per meter. How much force would it take to stretch by 15 centimeters? First off, we have to know that centimeters isn't the unit we want. We want to make sure that we're matching this meters, so we convert it to meters. So we have 0.15 meters. Now our equation Fe equals kx, and we just get 40.0 newtons per meter times 0.15 meters, which comes out to be exactly 6, but with sig figs we have to have 2, so we get 6.0 newtons as our elastic force. And that's really all that we have to look at. So you can see here we've got 3 examples to practice from these ones, and then 3 more in the workbook. So take a look at those problems. We'll go over them in class, and we're also going to do a lab that investigates how to weigh something using a spring after you know what the spring constant is. So look forward to that in class, and physics is awesome.